pieces of a puzzle objectives. And we've got functions and their properties, and you guys know a lot about functions already. You know, today is going to be a lot of reminder of things that you already know about functions. So we will be able to represent functions numerically, graphically, and algebraically. We will determine the domain, both implied and relevant, and the range of the function. So implied and relevant is a little bit different than what we've talked about in the past, and that's because we're now going to start talking, okay, but what if this is real world when we talk about domain? Determine if a function is continuous or discontinuous, and the type of discontinuity. Is it removable? Is it non-removable? Is it a jump? Is it infinite? Is it a whole? You know, all of those good things that we talked about in Algebra 2. Determine whether a function is increasing, decreasing, or constant. And we talked about that in a teeny bit in Algebra 2. It's not a hard concept. It's just something where you had so much that we were already teaching about functions. We're going to hang on and teach them a little bit more in pre-calc. And then determine if a function is bounded or unbounded. That would be, brand new, because Algebra 2 we don't teach bounded and unbounded. Local and absolute mins and maxes. You've done local mins and local maxes before, but we've never talked about absolute. It's a very easy concept, but we just have to talk about it. Determine if a function's symmetry is even, odd, or neither. So that's just new language to you about even or odd, symmetry or neither. And then determine if a function has any vertical or horizontal asymptotes. We're going to talk about the same things that you did in Algebra 2, but at a different level, because we want to talk about it as, okay, now we're going to go on to calculus, so what's an easier way to think about this process rather than memorize it? And then analyze the end behavior of a function, which we did in Algebra 2. So a lot of this is just going to be pulling things out of your memory banks and putting them together again, but some of this will be some new pieces. So right off the bat, we need to know what a function is if we're going to do all this talking about functions. So the definition of a function in pre-calculus looks a little different than the definition of a function you had in Algebra 2. I will tell you that most of the time I just use that Algebra 2 definition because it's so basic. For every input, there is exactly one output. So a function is a relation between two variables whereby each independent variable in the domain. So the domain is the x's, the inputs. And when we make a table and we go to graph something, we get to choose those. So that's why that's independent. We choose those, not anybody else. The person that's doing the graphing determines what goes into their table. However, once you put those into the function determines what comes out. So the dependent variables are the range. Your independent is your x's, your inputs, and your domain. Different names for different uses. And then your dependent variable is what's coming out of there. So it's the range, it's the y's. And it is something we don't spend a lot of time talking about, but it's one of those things that because we talk about domain, we also want to just touch on language as well. So what do we have here? Well, it is the easiest to think about this function that's going on right here in the middle here as a juicer. This is a juicer machine. So the domain of the juicer, the independent variables, is not just anything. It has to be things that you take out the manual, and the manual says you can use these fruits and vegetables. Those are the things that are in the domain of this juicer. Now, if you've got a toddler around the house, a little brother and sister, they might try to put their little wooden block into your juicer. Things will not go well. Now, that little wooden block has a name, and it's called a pre-image. Because somebody that doesn't know any better is going to try to put anything and everything into this. So a pre-image would be a wooden block. It won't go well. It won't be covered under warranty because you're not supposed to put wooden blocks into a juicer. It isn't supposed to happen that way. In the domain of the juicer are apples, bananas, cantaloupe. I'm not big on putting vegetables in the juicers, but celery, carrots, all that kind of stuff. So that's what you get to pick. And then you put it into this nice function, which is a juicer, and out it spits your dependent variable, your range, your y. And hopefully you like the taste of that. If you don't, you go back to your domain and you figure out, okay, it's not sweet enough. I'll put something that's sweeter in here. And you go after it again. But you don't control the taste. You just control what goes into it. And the juicer takes care of everything from there. that's what we need to think of our functions as being, because sometimes we want to put things into them that really should not go into them. And what that means is we're actually talking about pre-images. We're not talking about things that are in the domain. So if we use our definition of a function, for every input there's exactly one output. We have different types of mapping diagrams that show up in books. This is, I don't think you've seen any like this. It's just kind of weird because your Algebra 2 book, which is also published by Pearson, gives you mapping diagrams with kind of rounded off rectangles to go by. This one kind of looks like kidney beans. I don't know why they're doing that. So what we have to make sure is for every input, only one number for the output. So as I look at x sub 2, I follow the arrow and I see, yep, one output, y sub 2, that's it. X sub 1 over here, y sub 1, one output, that's good. X sub 3, y sub 3, one output, y sub 3 is it. X sub 4, y sub 3, one number, that's a function, it works. You put each of those x's in and you get one output. For every input, there's exactly one output. So now I go to the next one, and there's one that concerns me right away, and that is x sub 1. Because it has two arrows going away from it, which generally will indicate we've got two different numbers. This is y sub 1, and this is y sub 3, and that is two outputs. That one is not a function. Not going to happen. It doesn't mean that it isn't. Remember, everything that we graph is called a relation. So you can graph anything. It just doesn't mean that it's a function. So functions are special, and we want to make sure that we're working with those special features. Because with functions, there is certain math that we can do that can't be done with non-functions. So we need to know the difference. Now, if we want to know does y equals x squared, define y as a function of x, well, the first thing I get in my head is a visual. I can't help it. Y equals x squared. That's your parent function from exponential algebra. For a quadratic, it's a parabola. So I look at that and I think vertical line test. Yes, it passes. This is a function. But it's not the only way to figure out whether or not that's a function. You certainly could graph it and look at your table and make sure that each one of these x's gets mapped to just one y sub 1. Now, how would you know if that's not going to happen? If on your calculator there showed up an entirely different set of numbers in y sub 2. And you'd be going, wait a minute, I just put one function in there. What on earth is going on? Why am I getting two different sets of stuff? Well, that would mean it's not a function when that happens. And generally, that's going to come from something like this. Because if we put x into y equals plus or minus the square root of x, it's going to kick out two answers. So that's when we're going to know, hey, this isn't going to be a function. Like I said, graphically, easiest thing to do, vertical line test. You know, that's going to pass the vertical line test. If I draw a vertical line anywhere on this graph, it only touches the graph in exactly 1 point. So it's passing the vertical line test. Now, analytic, algebraic, we look at it and we just say, okay, f of x is fancy language for the output, for the range. Put a couple of numbers in and make sure things are going to work out. If I put a 1 in there, I get 1. One number, that's it. So I try to think, are there any numbers I could put in there and square them that would give me more than one answer? And there aren't. It just isn't. You think your way through it. So any way that we go about it, as long as we can reach the conclusion that, yeah, this is a function, we're good. So I know a lot of people, especially when we're doing these graphically, we're going to be talking about the visuals, but we do need to know how to deal with the numbers as well. So example 1 says, determine if the following represent functions. If not, explain why. So I'm looking at A. And initially, there's a lot going on there, so I'm kind of worried. But if I put negative 3 in, I get 3. I put negative 2 in, I get negative 6. Negative 1 gives me 0. 0 gives me 15, and 1 gives me negative 1. This is a function. For every input, there's just one output. I look at B. That's concerning. What on earth is going on there? Well, all of these numbers are different. If you put a negative 3 in, you get a negative 6. That is just one number. If you put a negative 2 in, you get a negative 6. It's just one number. So even though this definitely has that look of, boy, I better take a second look at that, that is a function. It's still And then we get to C, and something jumps out at us. Which number in the domain is bad here? 1. Yeah, so this is a no. Every input does not have just one output. And I would probably put a 1 in parentheses there, so if there's somebody thinking, well, which one are they talking about here? They can immediately go to the 1. Oh, yep, I see it. Put a 1 in, you get a 0, and you get a 15. That's a problem. Then we get to D. And this is the first time you guys have seen something like that. Okay, why is that 16 hanging out right here? That 16 is a T-bone steak. Are you supposed to put T-bone steaks into your juicer? So somebody figured that out before they put it in there. It's not supposed to go into it. That's a pre-image point. It is not in the domain. So if it's not in the domain, we really don't even need it here. We just check the rest of the points and make sure they're all okay. So if we check the rest, are we good? Yeah. Can't be put T-bone steak in the juicer. That would be silly. So we've got our domain, but one pre-image point that just shows us people are going to try to put anything they want into our formulas, but we have to let them know, hey, this is not going to work. You can't use this. Now, E and F, this is more like what you see in Algebra 2 when you put your tests in there, a list of ordered pairs. So go through that. Do you see any problem with E? What number is an issue? 6. Yep. So this would be no. Not every input has exactly one output. The 6 is bad, and it is just the 6. The 3 is good, the 2 is good, the 8 is good. It's just the 6 that's bad. How about F over there? Is that a function? No? Got a number that's a problem, that one? 5? Yep. No. Same reason. Not every input has exactly one output. Parentheses 5. The rest of them are good. Just not the 5. So in numerical form, as long as we know what we're looking for, we can still check and see whether or not they're functions. So this one says seeing a function graphically. So now we've got the visual sitting right there. Looking at these. Is A a function? That'll pass the VLT, vertical line test. Charlie Brown's shirt in B. Function? It's a function. It's good. How about the squiggly in C? No go. No. Why? It fails the VLT, the vertical line test, which I want to say learned for the last 2 years, but it's quite possible exponential has been a lot for you guys. So maybe, but just say last year was it. So vertical line test. A graph is a set of points XY ordered pairs in the XY plane, so Cartesian coordinate plane. Defines Y as a function of X if and only if no vertical line intersects the graph in more than one point. 1, that's it. You get 2, you're done. So thinking about C, it's because this graph wraps around on itself again vertically that it causes a problem. And folks, MCA, ACT always put at least one graph on those tests and say, is this a function or is it? So it's just a basic question. They want to know, do you remember what a function is or not from a graph? So now this says you try, which would be a good thing to do. However, I don't have time for candy partners. So what I want you to do is go ahead and do A, B, C, D, E, and F, and then check in with a chicken wing elbow partner and see if you've got the same yeses and no's that they do. You've only got the one no where. Which one's no? B. Yes. No. Fails. The VLT. Yes. 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 than the controversial one because this is an open dot. Remember, open dots are just to help us when we put our boundary lines on something. It's not included in the actual solution. So if you draw your vertical line right there, this point is hit, but this isn't because it was an open dot at that point. So this is a yes. It is a yes. You have to look really, really close, but it is. So in order to graph the equation, we have to have the equation explicitly solved for y. That's a big piece of what we're going to do when we talk about whether or not we have a function or not. This means we have to have y by itself on one side and an expression on the other side that has no y's. Because really what we're looking for is that we have to take an even root while we got y by itself. Because if we did, then we have to do the plus or minus piece. And that's going to tell us something's not a function. So let's take a peek at these. Determine if the following represent functions, if not, explain why. All right, let's take a peek. Got to get y by itself is what they said. So that would mean we're going to subtract 3x from both sides. Square root, and there it is right there. Y equals plus or minus the square root of negative 3x plus 6. So this is a no. Every input is not producing exactly one output. Now, first hour, I started to write an explanation down, and then I had to stop myself because I said, no, every input is not producing exactly one output. Because there's one, I was going to write, no inputs produce just one output, but that's not true. There is one number that would produce just one output. What would we need to have happen underneath here to just get one output? 0. Yeah. So there is one that works, but and they all have to work, and that's not happening here, that's for sure. Looking at B, things have gotten a little weird. We've got a couple of things with y in them. So let's move the thing that doesn't have y in it over to the other side. Just subtract the 4. Just solve for y. That means I have to separate y from the other stuff. How can I separate y? Factor. Yeah, pull y out by factor. Now, if you're looking at that, you should be saying, that's bad factoring. We could also take the 2. No, we don't want to take the 2 out. Remember, we're trying to get y all by itself. So now all we'll do is divide both sides by 2x squared minus 8. Like so. And we'll look around for a plus and minus. Do I get 2 outputs out of that thing? Nope, this is a function. So this is a yes. That's good. We didn't have to take the even root while we were doing that. Now, C is apparently different from your packet, so there's another one that got changed. I'm going to change this back. We need to see this example. It has something interesting and different in it. And that is that 3/2 power right there. Now that should bug us. What does that 2 on the bottom mean? It is a square root. So if it's a square root, this is out. Because of that. So it's an even root. So that's the way we're going to tell right away when something like this happens. So with this one, I would probably stay away from, every input doesn't have exactly one output, and would say something more about how we would definitely have to restrict the domain on this one. And the reason is because we have to be able to take the square root. So no, the domain would be restricted. So the question is, why not solve for y? We could. I went through and did this one. It's nasty, but we could. But what happens is we kind of go in and out of the domains needing to be restricted and not as we do the problem. So it's better to just stop and say, oh, I see a square root right there. Nope, not going to be a function. D. Well, y is almost by itself. How do we get by itself? We square both sides. Function or not? That's the first one we started with. That's your basic parabola there, your parent function for a parabola. So that was a go. There was no square rooting as we went through any of that. So, like I said, we're going to spend a lot of time today on the objective about domain and range here. Determine the domain implied and relevant and range of a function. We'll spend the rest of the time actually doing this. So, note, when a function is described algebraically, use the formula to determine the implied domain. We're given x's and y's all the time. We don't know what the formulas are for. They just plop them in front of us and say, here's a formula, tell us the domain. When they do that, we use the implied domain. We don't know what they're using it for. We don't know if there's a real world application going along with it. So, a lot of them will just say use all real numbers if there's no restrictions at all. And then the second part of this says if the formula is being used to model a real world situation, use what's called the relevant domain. So, with this one, it's x's and y's. We don't know what they stand for. We just go ahead and do the domain. But with this, we should recognize that formula. That's what they're saying. We should know what that formula is for. What's it for? Area of a circle. So, somebody that knows absolutely nothing about geometry comes up and says, I'm going to say r is negative 16. You would say, stop. Why? You can't have a negative radius for a circle. That doesn't make any sense. So the implied domain for this is all reals. If you don't know anything about what this formula is for, you could say, I'm going to put whatever number I want in there. I don't care. It's a formula like any other formula. But once we know what it is, the relevant domain is, hey, wait a minute. You've got to use r values that are greater than or equal to 0. Now, some people would argue, shouldn't it be greater than 0? Because what are you using that formula for if you don't have a radius? But we're just going to not overthink that and say the radius has to be greater than or equal to 0 in that formula. So that's relevant domain. We recognize the formula. We understand there are words that go along with it, which generally means it's real world. And we have to think a little bit more about our domain. For example, we can define the volume of a sphere as a function of its radius by this formula. V of r equals 4/3 pi r cubed. You should recognize that from geometry. That long ago. And it says, note, yeah, this is kind of silly. Note that this V of r, this is not multiplication. It's not V times r, but we all know that. This formula is defined for all real numbers, but the volume function is not defined for negative r values. It wouldn't make sense. How are you going to have a sphere that has a negative radius? That doesn't make any sense. So if our intention were to truly study the volume function for a sphere, we would restrict the domain to be r is greater than or equal to 0. Jeopardy question, by the way. We had this up there once. What is this the formula for? So a little trivia action there. It's smarter than a 5th grader. Are you smarter than a 5th grader? Yeah, those kind of formulas on there before. To find the domain of a function algebraically, we must look for values of x that don't work and tell people you can't use this one. Now, I'd like to tell you can use any number you want to, but we can't. First of all, we've covered this already, dividing by 0. You can't divide by 0, so you have to tell people, this number's out because it'll make you divide by 0. You can't do that. Take an even root of a negative number. We can take an even root of 0. We can take an even root of any positive real numbers, but not negatives. That'll make us leave the real number system. We'll be into imaginary. We're not going to do that. And then notice these are in blue because those are the ones we're going to focus on. In the black here, it says taking the logarithm of a non-positive number, and then it says we're not going to worry about this until later in the year. But I do want to show you this so you can remember why this is happening the way that it is. Let's say we're asked to evaluate the logarithm base 4 of negative 81. what we would do is say, well, I don't know what that is. So I'm going to make this equal to x, and I'm going to exponentiate. And how we exponentiate is by taking a snail shell and using that to guide us as we're writing this in exponential form. So we'll say 4 to the x equals negative 81. Other than magic wand, we don't have a power that we could raise 4 to that would make it negative. It doesn't exist. And so this is another situation where we'd have to say, we can't be doing the negatives here. We can't evaluate negative logarithms for a positive base. But like it says, that's later. We won't get to logarithms until later. So now we're going to jump right in. And we are going to find the domain of each of these functions. It says express in set notation and interval notation. I want to remind you that this really means set builder notation right there. So we're going to do both of these. Set builder notation mostly is just a reminder so you guys don't forget about set builder notation. And it actually leads us to our interval notation. So I look at A, and I see I'm supposed to take the square root. And I realize I can take the square root of 0, and I can take the square root of positive stuff, but not negatives. So that x plus 3 is going to have to be greater than or equal to 0. I'm just going to solve that little inequality by subtracting 3 from both sides. And I've actually done most of my set builder notation when I've done that. But I need to introduce you to some new notation, and that's just going to be domain notation, and I'll talk about range notation. We use a great big capital D to stand for domain. And then what we do is use a little subscript so that people know which function we're talking about, since this is an F. Domain of F. Capital D with a little f. If we were doing the range of F, we'd do capital R, little f, for a subscript. But we're just going to do the domain. So set builder notation, we have the Richard Nixon brackets. X is defined as, and then x is greater than or equal to negative 3. So like I said, usually when we're solving these, we're thinking in set builder notation anyway. But then we have to do interval notation. And that's not so bad, because this is going to start at negative 3 and go on to the right forever. You just think number line. So negative 3. Infinity. And if you wanted to be really fancy, you could put d of f down here by this one. But what I usually do is just put d of f once, and then have both the set builder and the interval notation up there. Then it's pretty basic to follow. Say, oh yeah, I see now. They just spoke that in interval notation. Oh my, g of x. G of x has some issues. First would be, it's got another square root in it. So right up here, we see that x has to be greater than or equal to 0. But this one has another issue. There's a number we have to tell people they can't use. What number is it? 5. Yeah, you can't use a 5 down here. So how are we supposed to do that for the domain of G? Well, we do exactly what we just said. We have set builder notation for x. X is greater than or equal to 0. But then we put a comma to let them know, hang on, I got something else for you. You can't use a 5. So x is greater than or equal to 0, but x can't be 5. So the not equal to equal sign with a slash through it. And then our set builder notation gets a little interesting. We think number line. All right, we can use 0, 1, 2, 3, 4, but then we got to jump over 5. So I'm going from 0 to 5. Can't use 5. Jump over it with a U, and then continue on, and you'll be okay. So whenever we jump over, we're going to say, hey, don't use this number, use those parentheses, and then use a union to show people, hey, these are together here. Don't stop. We're not done. Then, C says A of S, and I don't like the way this is written. Square root of 3 over 4 S squared. Hopefully you remember that is the formula for the area of the equilateral triangle with a side length of S. So square root of 3 over 4 S squared. So if we know what this formula is for, we want relevant domain. So how do we restrict S? What can you use for S's? 0 and any positive. So we just say S is greater than or equal to 0. 4, so we would be domain of A, set builder notation, S slash S is greater than or equal to 0. But we know what this is for, that's why I'm not. It's the relevant domain, especially if we know what the formula is for. We want to give them the numbers that they really should use in the formula. And since this is going to be the side length of a triangle, negatives are out. You're right for the implied domain. If we didn't know what this formula was for, then we'd go down. And then this one, we would just do interval notation of 0 and on for an infinite length of the side. There it is. And now we have 2 more pages of this. We probably won't get through them all. We're going to go through whatever we can in the time that we have, and then whatever's left, I will look to see if there's anything goofy in the other ones, and then make sure that we talk about those tomorrow. But let's get through what we can while we're here. Extra example 3 says, find the domain of each of the following. State your answer in set or interval notation. So I look at A, 3x on the top, hey, all real numbers. But it does have a denominator, and that means there's probably some zeros down there that we need to deal with. So how are we going to figure out where the zeros are for that denominator? Well, let's factor that little puppy. Let's see what happens. All right. Come up with 2 numbers that multiply to -6 and add to 1. What are they? -2. So we have to tell people you can't use -3 and you can't use 2. And we need to do that in set builder and interval notation. So this is the domain of F such that x is defined as x can't be -3 and x can't be 2. And if you're thinking to yourself, shouldn't we put something about all real numbers in there? It's implied. It's all real numbers unless we tell them otherwise. So leave out the -3, leave out the 2. Which means we're going to have to do some jumping. So negative infinity, and which of those is the first one we hit on the number line left to right? -3. Got to do some jumping over -3. Then where do we go? Up to 2, but then we have to jump again. And on forever. So you just have to think as you go through that, think number line the whole way. Okay, I'm good till I get to here. Now I'm going to jump and go to the other side. Oh, B. That's interesting. Because not only is our denominator factorable, but so is our numerator. Huh, let's see what that looks like. So this will be 3 times the quantity x plus 4. How's x squared minus 16 factored? X plus 4, x minus 4. Now, this would be huge if we were graphing, because it tells us there's going to be a hole in our graph at x equals -4. But we're not graphing. We are talking about restrictions in the domain. So it still comes down to, while it's great that the numerator was factorable, we don't really care. What we care about is the numbers they can't use in the bottom, and the numbers they can't use are -4 and 4. So the domain of G, all x defined as x can't be -4 and x can't be +4. And if you want to write it x not equal to +n minus 4, that's perfectly okay. I just want to make sure that we've got everything in the notes. Well, that's going to be some interesting interval notation. What are we going to have to do for our interval notation for this one? Can I just put negative infinity to infinity? What are we jumping over? The -4 and the 4. So negative infinity to -4, union with -4 to 4, union with 4 to infinity. So there's our jumps. In fact, you know what? Since you're not talking, what I want to do is 4, 3, 2, 1, 0 you right now. On how do you feel about the interval notation when you have to make the jump? It'll get there. It'll get there. We have to leave that number out that we cannot use. And remember, those parentheses are showing, hey, we're going super duper close to this. We're going to do 3.9999999. Just not 4. Can't do 4. It'll make it a 0 in the denominator. Hey, can we put all real numbers for C? Why not? A square root has a square root. So 2x minus 3 is going to have to be greater than or equal to 0. It could be 0 because the square root of 0 is 0. So we would add 3, and we would divide by 2, and it would look like that. And we would say, well, that was a nice, easy little, that's over half of our set builder notation right there. So domain of H, x is defined as x is greater than or equal to 3 halves. Oops. And the interval notation, pretty nice too. Square brackets, 3 halves, on forever. That wouldn't be too bad. So D must not be too bad, because it's the same kind of thing. So in this one, 3 minus 5x has to be greater than or equal to 0. All right, we'll subtract 3. And then, oh, what's the interesting thing that happens in this step? Divided by a negative, so what do we have to do? Flip the sign. Oh, that's interesting. So now we have x is less than or equal to 3/5, and that is the domain of P. X such that x is less than or equal to 3/5. Like so. So, can we put negatives in this one? Yeah, we can. We don't know what that formula is for. I have no idea where that came from. So for the implied domain, we're going to be negative infinity on up to 3/5, including the 3/5. Well, we don't know what that formula is for. So we just have to say, hey, it's x's and y's. We're going to do the best we can. Alrighty, let's look at E. Oh boy, that's the mother load of domain issues right there. Not only do we have a square root, we also have a denominator. So, let's go after the numerator first. Can be 0, can be positive. 2x greater than or equal to 1, x greater than or equal to 1/2. All right, that's not a big deal. So let's try and factor that denominator and see what happens. Did you come up with two numbers that multiply to negative 10 and add to negative 3? So that means we have to leave out 5. We have to leave out negative 2. Hey, wait a minute. One of those is not relevant. We just did some math we didn't have to do. Which one? Yeah, we already knew we couldn't use negative 2. Right here, x is greater than or equal to 1/2. So we put 1 slash through that because we want Mrs. Cedarholm to see it on our paper. Okay, I knew that, Mrs. Cedarholm. I knew that. And then we write our set builder notation. So this is, yeah, we're just going to have to use D. This one didn't have a D. So the domain of this one, set builder notation, x such that x is greater than or equal to 1/2, comma. Let them know there's more coming. Don't use the 5. Don't use the 5. All right, since some of the numbers that I saw earlier for the interval notation I didn't like, you're going to help me out more with this one. So we're going to do x is greater than or equal to 1/2, but we've got to jump at 5. So how do we start? Square bracket, 1/2. To where? Up to the 5. Then what? Parentheses, union, parentheses. So that's going to make that jump happen. To where? There it is. So we had this equals bar dealing with the 1/2. We have to include that, but we've got to jump over that 5. Okay, we'll start with F, because F has some interesting stuff going on. And then, like I said, I'll just kind of pick anything that had strange stuff. Oh my goodness, this is the long section. There we go. So, ignore that. It's just 1 through 20. That's it. That's why I said tonight would be a great night for those of you that need to finish up 1-1 and get that blue worksheet done and catch up. Do this one. So, lots of objectives in what we're doing today.